Here is your text with proper punctuation, paragraph breaks, and cleaned up grammar for clarity and readability. To fall into a black hole, and we have some imaginary spaceship that can take us as far and as fast as we want. So we get into our spaceship. What now? What is a black hole, and how do we find them? Essentially, what's the idea behind a black hole? Let's say you take the sun, a star with a massive sun, and you collapse it. You keep on collapsing it. You squash it down and squash it until its radius becomes just 3 kilometers. 3. If you artificially squashed all of that mass into that tiny little space, the gravity right at its surface would be immense. So immense that if you wanted to escape, the speed you'd have to travel to escape its gravitational pull, called the escape velocity, would exceed the speed of light. So even light rays emitted from the surface, if you could squash it down that far, would just stay there. That is a black hole, a spot so massive, with gravity so strong, that not even light can escape. At first, black holes were just a mathematical quirk, a weird solution to equations that otherwise seemed to fit our universe. They were only theoretical, but then we started to find them. Over decades, scientists measured the movement of stars, galaxies, and gases that were warped by seemingly empty patches of space. Left behind, we now know, by the collapsing death of stars much larger than our sun. We discovered that black holes are real. We now know they're all over our universe. Some estimates say there are up to 40 quintillion of them. Almost every galaxy has a supermassive black hole at its center, including our own Milky Way. Let's go. Let's imagine that we choose the black hole at the center of our own galaxy. Yeah, Sagittarius A star. I think it's called that. I know that we took this picture of it. What are we looking at here? So, the light. What is the light in this picture? It's not from the black hole, because we just said black holes trap light. It's from what's called the accretion disk. This is another way scientists have found black holes, by spotting their glowing accretion disks. You're to imagine material spiraling around in orbit around this very dense object, very violently orbiting. And so it heats up and emits light. Wait. So then why in this photo do we not see the accretion disk across the middle? Well, it turns out we happen to be seeing this particular black hole from above. But if you were to see it edge on, something very weird starts to happen. What we're seeing is actually the accretion disk in front of and behind the black hole. Because the black hole's gravity is so immense, it bends and distorts light around it. So imagine this disk of material around this thing. Light rays, from your perspective, even from behind the black hole, go around into your eyes. Sometimes they orbit and then reach your eyes from every point on the disk, underneath, on top, and behind. Light rays go around the black hole. That's what you see as the image. And in our little spaceship, we're getting closer. As we approach, I start to wonder, how big is this thing? Based on the way it pulls the stars around it, scientists estimate that the black hole at the center of our galaxy has a mass of 4.3 million times that of our sun. But if you plopped it down inside our solar system, this black hole would only extend to about 1/5 of Mercury's average orbit. So, it's shockingly small for its immense mass. And compared to other black holes, ours is just medium-sized. One of the smallest black holes ever found is J1650. Its diameter is only about as long as Manhattan, but it has a mass 3.8 times that of our sun. One step up would be the black hole in Messier 15. It's about twice the diameter of Earth, with a mass of 4,000 suns. Now we're at the lower limit of what's considered a supermassive black hole. This one is just under half the diameter of our sun, but about 100,000 times its mass. And here's Sagittarius A star. Now, to the truly insane, the black hole in the galaxy M87 weighs 5.4 billion suns. You could fit our solar system around 4 times across it. It was the first black hole we ever got a picture of in 2019. And then there's TON 618. It weighs 66 billion times more than our sun, and it could fit nearly 40 of our solar systems across it. But it might not be the biggest. Phoenix, it seems to have a mass of 100 billion suns. But since this black hole is closer, we're seeing what it looks like more recently than TON 618, which might have grown since. And these are just the biggest ones we know of. There could be an even more massive one just waiting to be found. And now, we're starting to get pulled into one. So we're falling towards this thing now. about when we're in the accretion phase. Will we be banged around by a lot of stuff? We might get in a bit of a mess as we fall through the accretion. You're absolutely right. It's a bit nasty around these things. But let's say our room, our spacecraft, is magically insulated from radiation, heat, and all those things. Then nothing. One of the most shocking things is that, from the point of view of someone outside, the description is very different. Now imagine you, yes, you watching this. You go outside and look with an all-powerful telescope at me and Brian falling into this black hole 26,000 light years away. What would they see happening to us? As we fall toward this thing, if they could see our watches, they would see our time tick more slowly, and then stop at the horizon. Stop. This is incredibly important. As we get closer to the black hole, there are now actually two journeys. Our journey as we see it, and our journey as you would see it from far away. And they are very different. Why? Because black holes distort space and time near them. And that's central. There's nothing weird about that. Well, actually there is, but not according to Einstein. Albert Einstein was the one who realized that space and time are actually one thing, space-time. And space-time is stretchy. It warps or curves in response to matter and energy. Einstein's theory says, give me a ball of matter, and the equations will tell you how the fabric of the universe is distorted. A black hole is the most extreme example of this distortion. Reality very close to a black hole and far from it are not the same. To us, it looks like the universe is speeding up. To you, it looks like we're in slow motion. Now we're crossing the line, where no light can ever escape to reach you again. For us, we don't feel it. But to you, you never actually see us cross it. Ever. Do you see us imprinted there forever? Or does our light just fade? That light, climbing away through this gravitational field, gets stretched. We get redder and redder, infinitely redshifted. From our perspective, there's no turning back. You can write the equations as a space being like a river flowing into a sinkhole in space. The river of space flows at the speed of light inward on the horizon, and faster than light inside. If you're a photon, a particle of light, you're like a little fish swimming upstream. But if the current is the speed of light, and you're swimming at the speed of light, you can't get out. We're now past the event horizon. We're still falling. And finally, we begin to feel something.